When installing a grounding electrode conductor to a bare metal underground water pipe using rigid metal conduit, several factors must be considered to ensure compliance with the National Electrical Code, or NEC. These considerations include the bonding of the conduit and conductor at both ends, the allowable extension distance of the conductor, the use of appropriate bonding methods, and the selection of suitable water pipe clamps. Addressing the bonding at the main switchboard, the 3/0 grounding electrode conductor can extend up to 6 feet beyond the neutral bus location where it connects as per NEC section 250.68. C2. A lug that screws onto the conduit and allows the cable to pass through is an acceptable method of bonding at this end. Regarding bonding at the water pipe, Celtet is generally not rated for bonding grounding electrode conductors. Looping the 3/0 wire through a bonding bushing or ground connector on the end of the conduit is typically the preferred method. However, an external ground clamp can be installed on the Celtet, but it must be listed for use with that type of conduit. Addressing the water pipe clamp, a 3/0 lug can be mounted to the mounting screw of a 1-inch water pipe clamp, provided the clamp is listed for that purpose. Another option is to use a ground rod clamp that is designed to accommodate a 3/0 conductor and mount it to the water pipe near the existing clamp. Several NEC code references are relevant to this installation. Firstly, NEC section 250.68. C2 covers the extension of the grounding electrode conductor. Secondly, NEC section 250.90. A3 addresses the bonding of metallic conduits. Thirdly, NEC section 250.64. A6 discusses acceptable water pipe clamps. To elaborate on bonding at the main switchboard, NEC section 250.68. C2 specifically allows for the grounding electrode conductor to be spliced or extended using a reversible compression connectors listed as grounding and bonding equipment, pressure connectors listed for grounding and bonding, exothermic welding processes, all listed connections devices or fitting that establish an equipotential connection between the grounding electrode conductor and the extension. The extension can extend to the first point where the grounding electrode conductor is connected to the grounding electrode system. The key is that the extension must be securely connected and provide a reliable, low-impedance path to ground. Considering acceptable bonding methods at the water pipe, looping the 3/0 wire through a bonding bushing or ground connector on the end of the conduit is preferred because it creates a direct, low-impedance connection between the grounding electrode conductor and the metal water pipe. This method ensures that any fault current will have a clear path to ground, minimizing the risk of electrical shock or fire. If Celtet is used, it is critical to verify that any external ground clamp installed on it is specifically listed for use with the type of flexible metal conduit. The listing indicates that the clamp has been tested and approved for grounding applications, and it will provide a reliable connection. Using an unlisted clamp could compromise the integrity of the grounding system. When selecting a water pipe clamp, it is important to ensure that it is listed for the intended purpose and that it can accommodate the size of the grounding electrode conductor. If a 3/0 lug is mounted to the mounting screw of a 1-inch water pipe clamp, the clamp must be listed for that specific configuration. This means that the clamp has been tested and approved for use with a 3/0 lug attached to the mounting screw. If the clamp is not listed for this purpose, it may not provide a secure and reliable connection. An alternative approach is to use a ground rod clamp that is designed to accommodate a 3/0 conductor. These clamps are typically larger and more robust than standard water pipe clamps, and they provide a more secure connection for larger conductors. They can be mounted directly to the water pipe near the existing clamp. A general grounding electrode system typically includes a grounding electrode, which is a conductive object that establishes a direct connection to the earth. Common grounding electrodes include metal underground water pipes, ground rods, ground rings, and concrete encased electrodes. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus or the neutral bus in the electrical panel. This conductor provides a path for fault current to flow back to the source, allowing the overcurrent protection device such as the circuit breaker or fuse to trip and de-energize the circuit. The grounding electrode system is essential for safety and proper operation of electrical equipment. It helps to prevent electrical shock, fire, and equipment damage by providing a low impedance path for fault current to flow back to the source. It also helps to stabilize the voltage in the electrical system and reduce electrical noise. When installing a grounding electrode system, it is important to follow all applicable codes and standards, such as the National Electrical Code. This includes selecting the appropriate grounding electrodes and conductors, properly installing the grounding electrodes, and ensuring that all connections are secure and reliable. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. NEC Table 250.66 provides the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 copper or 250 kc aluminum, the minimum size grounding electrode conductor is 2 AWG copper or 1/0 AWG aluminum. The grounding electrode conductor must be continuous and without splices. If a splice is necessary, it must be made using an irreversible compression connector listed as grounding and bonding equipment, a pressure connector listed for grounding and bonding, an exothermic welding process, or a listed connection device or fitting. The grounding electrode conductor must be securely connected to the grounding electrode and the equipment grounding bus or neutral bus. Connections must be made using listed connectors or fittings. The grounding electrode must be located as close as practicable to the service entrance. If a metal underground water pipe is used as a grounding electrode, it must be supplemented by an additional grounding electrode, such as a ground rod or ground ring. The supplemental grounding electrode must be bonded to the metal water pipe. Ground rods must be at least 8 feet long and must be driven into the ground at least 8 feet apart. They must be made of copper, steel, or other approved material. Ground rings must be at least 20 feet long and must be buried at least 30 inches below the surface of the earth. Concrete encased electrodes must be at least 20 feet long and must be encased in at least 2 inches of concrete. The concrete must be in direct contact with the earth. In addition to the grounding electrode system, an equipment grounding system is also required. The equipment grounding system provides a path for fault current to flow back to the source from non-current carrying metal parts of electrical equipment. This helps to prevent electrical shock if a fault occurs. The equipment grounding system includes equipment grounding conductors, which are typically bare or green insulated wires that run along with the circuit conductors. The equipment grounding conductors connect to the metal enclosures of electrical equipment, such as outlets, switches, and light fixtures. The equipment grounding conductors must be connected to the grounding electrode system at the service entrance. The size of the equipment grounding conductors is determined by the size of the circuit conductors. NEC Table 250.122 provides the minimum size requirements for equipment grounding conductors based on the size of the circuit conductors. For example, if the circuit conductors are 12 AWG copper, the minimum size equipment grounding conductor is 12 AWG copper. The equipment grounding conductors must be continuous and without splices. If a splice is necessary, it must be made using an approved connector. The equipment grounding conductors must be securely connected to the metal enclosures of the electrical equipment. Connections must be made using listed connectors or fittings. The proper installation of a grounding electrode system and an equipment grounding system is essential for safety and proper operation of electrical equipment. It is important to follow all applicable codes and standards when installing these systems. Grounding and bonding are critical concepts in electrical safety and system performance. Grounding refers to connecting electrical equipment and systems to the earth, while bonding involves connecting different metallic parts of the electrical system together to create a low impedance path for fault currents. Firstly, grounding provides a path for fault currents to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. This helps to prevent electrical shock, fire, and equipment damage. Secondly, bonding ensures that all metallic parts of the electrical system are at the same electrical potential. This minimizes the risk of electrical shock if a person comes into contact with two different metallic parts of the system. Thirdly, grounding helps to stabilize the voltage on the electrical system and reduce electrical noise. This can improve the performance of sensitive electronic equipment. The NEC provides detailed requirements for grounding and bonding in electrical systems. These requirements cover a wide range of topics, including the selection and installation of grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. One common application of grounding and bonding is in the installation of metal underground water pipes. As mentioned earlier, metal underground water pipes are often used as grounding electrodes. However, they must be supplemented by an additional grounding electrode, such as a ground rod or ground ring. The water pipe must also be bonded to the electrical system using a bonding jumper. Another common application of grounding and bonding is in the installation of metallic conduits. Metallic conduits are often used to protect electrical conductors from damage. However, they must also be bonded to the electrical system to provide a path for fault current. Bonding of metallic conduits can be accomplished using bonding bushings, bonding jumpers, or other approved methods. Grounding and bonding are essential for electrical safety and system performance. It is important to follow all applicable codes and standards when installing grounding and bonding systems. Proper grounding and bonding practices can help to prevent electrical shock, fire, and equipment damage, and can improve the performance of electrical systems. The selection of appropriate grounding and bonding equipment is critical for ensuring the safety and reliability of an electrical system. There are many different types of grounding and bonding equipment available, each with its own specific application and performance characteristics. Grounding electrodes are used to establish a connection to the earth. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically made of copper or steel and are driven into the ground. Ground plates are typically made of copper or steel and are buried in the ground. Concrete encased electrodes are made of copper wire or rebar and are encased in concrete. Grounding electrode conductors are used to connect the grounding electrode to the electrical system. Grounding electrode conductors are typically made of copper or aluminum and are sized according to the size of the service entrance conductors. Equipment grounding conductors are used to connect the non-current carrying metal parts of electrical equipment to the grounding system. Equipment grounding conductors are typically made of copper or green insulated wire and are sized according to the size of the circuit conductors. Bonding jumpers are used to connect different metallic parts of the electrical system together. Bonding jumpers are typically made of copper wire or strap and are sized according to the size of the equipment grounding conductors. Connectors and fittings are used to make secure and reliable connections between grounding and bonding conductors and equipment. Connectors and fittings must be listed for grounding and bonding applications. When selecting grounding and bonding equipment, it is important to consider the following factors. Firstly, the type of electrical system. Secondly, the size of the electrical system. Thirdly, the environmental conditions. Fourthly, the applicable codes and standards. By carefully considering these factors, it is possible to select the appropriate grounding and bonding equipment for a particular application. Proper installation of grounding and bonding equipment is essential for ensuring the safety and reliability of an electrical system. The NEC provides detailed requirements for the installation of grounding and bonding equipment. These requirements cover a wide range of topics, including the selection and installation of grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. When installing grounding and bonding equipment, it is important to follow all applicable codes and standards. It is also important to use qualified personnel who are familiar with grounding and bonding practices. Improper installation of grounding and bonding equipment can create a serious safety hazard. It can also lead to equipment damage and system malfunction. Regular inspection and testing of grounding and bonding systems is essential for ensuring their continued effectiveness. The NEC recommends that grounding and bonding systems be inspected and tested at least every 3 years. Inspection should include a visual examination of all grounding and bonding conductors and equipment. Testing should include a measurement of the resistance of the grounding system. If any problems are found during the inspection or testing, they should be corrected immediately. Proper maintenance of grounding and bonding systems can help to prevent electrical shock, fire, and equipment damage. It can also improve the performance of electrical systems. Grounding and bonding are essential for electrical safety and system performance. By following proper grounding and bonding practices, it is possible to create a safe and reliable electrical system. Remember that cell-tight, or liquid-tight flexible metal conduit, has specific limitations regarding its use as a grounding conductor. While it can be used in some situations, it's crucial to understand its limitations to ensure compliance with electrical codes and maintain safety. Cell-tight is often used in applications where flexibility is required, such as connecting motors or other equipment that may vibrate or move. However, it's not always suitable as a primary grounding conductor. The NEC specifies the conditions under which liquid-tight flexible metal conduit can be used for grounding purposes. Generally, it's permitted in sizes 3/8 inch through 1/4 inch where the circuit conductors are protected by overcurrent devices rated at 20 amps or less for 3/8 inch and 1/2 inch sizes, and 60 amps or less for 3/4 inch, 1 inch, 1/4 inch sizes. For trade sizes 1/2 inch through 4 inch, it can be used to bond raceways that contain service entrance conductors. The length of the liquid-tight flexible metal conduit is also limited. It should not exceed 6 feet in length. If the liquid-tight flexible metal conduit is longer than 6 feet, a separate equipment grounding conductor must be installed. The ampacity of cell-tight as a grounding conductor is relatively low compared to other types of conduit, such as rigid metal conduit or intermediate metal conduit. This is because the metal wall of cell-tight is thinner and has a spiral construction, which increases its impedance. Because of its limited ampacity, cell-tight is not suitable for grounding high-current circuits. In these cases, a separate equipment grounding conductor must be installed. When using cell-tight, it's important to ensure that it is properly installed and connected. The fittings used to connect cell-tight to other equipment must be listed for grounding purposes. The connections must be tight and secure to ensure a low impedance path for fault currents. In situations where cell-tight is not suitable as a grounding conductor, a separate equipment grounding conductor must be installed. This conductor can be run inside the cell-tight or outside, depending on the application. The equipment grounding conductor must be sized according to the requirements of the NEC. When a separate equipment grounding conductor is installed, it must be connected to the grounding electrode system at the service entrance. This provides a path for fault currents to flow back to the source and trip the overcurrent protection device. It's also important to ensure that the cell-tight is properly bonded to the equipment it connects. This can be accomplished using bonding jumpers or other approved methods. Bonding helps to ensure that all metallic parts of the electrical system are at the same electrical potential, which reduces the risk of electrical shock. Always consult the NEC and local electrical codes for specific requirements regarding the use of cell-tight as a grounding conductor. These codes provide detailed guidance on the conditions under which cell-tight can be used for grounding, as well as the requirements for installing separate equipment grounding conductors.